Is my screen visible to everyone?
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay. Okay, so today we will look at another series which is known as the Lorenz series. Okay, just before we go to Lorenz series, we'll just recollect whatever we had done about the Taylor series. We first saw what a Taylor series is, how to obtain a Taylor series using the coefficients for a Taylor series using this formula. Then we did the convergence of a Taylor series. Okay, we understood what is the meaning of the convergence and how we can find out the radius of convergence by using two formulas. One is known as the ratio test, another one is the nth root test. Okay, and then some problems I had given to you all. Now, there is another kind of series which is known as the Lorenz series. Okay, now what is the difference between Taylor series and the Lorenz series? You see, you'll have a Taylor series if and only if the function is analytic at all points within a certain neighborhood of a point. Okay, the Taylor series expansion will be applicable if the function is analytic at each and every point in a neighborhood. Okay, about z equals z naught. Okay, so then only we will have. So if I have a disk, so within this disk, okay, within the shaded region, the Taylor series is applicable. That means there are no singularities. It's guaranteed that there are no singularities within this region. Okay, but what if there is a singularity? What if I have a disk and inside the disk there is a point where there is a singularity? At that point, can we get a Taylor series? Obviously not. But can we get some kind of a series representation? Yes, we can. Okay, and that series representation is known as the Lorenz series. Okay, so if f, this is how in general this is how the region looks like. The shaded region is the region over which the function f is analytic. Okay, so this shaded region, the function f of z is analytic. The function f of z is analytic in this shaded region. So function f is analytic on the outer circle as well as the inner circle. That is, it is not only analytic in this region, it is also analytic in the outer circle, this one, as well as in the on the inner circle. But it need not be analytic in this region. There is a point in this region, that point is z naught, and in this point z naught at least, the function is not analytic. Okay. So, so we have this function which is analytic in this region, and okay. So then we can write down this function f of z. We could write down this as a series expansion like this. You see, it looks very similar to your Taylor series, but no, there is a difference between this and what happens in the Taylor series, because in the Taylor series, if you look back at the Taylor series expansion, if you look back at the Taylor series expansion, Taylor series, what happens? A n z minus z naught to the power n. This is same as the Lorenz series. Okay, what you are the whatever is there inside the summation a n z minus z naught to the power n, that is the same in the Lorenz series. A n z minus z naught to the power n. The difference between Taylor series and the Lorenz series is, in Taylor series, you see, n starts from 0 and goes all the way till infinity. So n takes only positive values. So this power n, it takes only positive values. But in case of Lorenz series, that does not happen. In case of Lorenz series, n can take negative values also. Okay, so let me write this down here. In Taylor series, in a Taylor series, this function f of z is written as the summation. Inside the summation, exactly the same as here. So we will have a n z minus z naught to the power n. Only thing is, instead of n starting from minus infinity to plus infinity, here n starts from 0 and goes all the way till infinity. So it means n is always positive. Okay, n is always either 0 or positive, or in other words, n is non-negative. But here n can take negative values also. Okay, so once that happens, what we can do is we can always split this into two parts. We can always split this into two parts, because you can see here, over here, I could just write this. Okay, we could just expand it like this. We could expand it like this. There is f of z. We could expand this. So let's say n equals 0. If I take n equals 0, so we have a0, z minus z naught to the power 0 is anyway 1. The next one will be a1 z minus z naught. Then we have a2 z minus z naught squared, and so on. And on this side, because we are having negative values, so here you see n equals this, n equals 0 here, n equals 1 here, n equals 2 here, and so on. Here on this side we'll have n equals minus 1. So when we have n equals minus 1, so a minus 1, a minus 1, a minus 1, z minus z naught to the power minus 1, that is divided by z minus z naught. Likewise, for n equals 2, n equals 2, so we have a minus 2, and this is divided by z minus z naught squared, and so on. This is what we have. So now what we do is we split this into two parts. The same series, we said no, let us split this into two parts. Okay, this non-negative part, that is this part, this non-negative part, let us just represent this as instead of a naught, a1, and so on, let's just call it as b0 plus b0 plus b1 into z minus z naught. We are just renaming this. This a0, I'm just calling it as b0. a1, I'm calling it as b1. Okay, a2, I'm calling it as b2, z minus z naught squared, and so on. So this is what you get. Okay, so m goes from 0 to infinity. Likewise, the other one. Okay, likewise, on the other side we have the negative values. Okay, the negative indices. So these negative indices, a minus 1, I'll call this as cm. A minus 1, I'll call this as, let's say, c1. Okay, a minus 1, I'm renaming it as c1, divided by z minus z naught, plus a minus 2, I'm calling it as, I'm changing its name, and I'm calling it as c2, divided by z minus z naught whole squared, and so on. Okay, so basically we are collecting this part. We're collecting this part, and this gives us another series. So this is the series. So we have one series which contains only the positive powers of z minus z naught, another series which contains only the negative powers of z minus z naught. Okay, so we could express it like this. So once we get this, we can now find out the coefficients. Either you can find out the coefficients of a n directly, or you can find out the coefficients bm and the cm separately. Okay, so the coefficient bm is given by this. The coefficient bm is equal to 1 by twice pi I. Then you have to integrate over some contour, some contour c. This contour c, it lies within this. By the way, this region, this shaded region that we have here, this shaded region is known as an annulus. Okay, so when I say annulus, this is what I mean. This shaded region, that we have. Okay, so this shaded region is known as the annulus. Okay, this is known as the annulus. So we have a contour C which lies completely inside this annulus. Okay, then over this contour C, you integrate the function, I'm using a dummy variable omega. Okay, I'm using a dummy variable omega because I don't want to use z here, because I'm using z over here for the function. So I find the line integral of the same function over this contour divided by omega minus z naught to the power n plus 1. So when I read, that is going to give me my bm. Okay, that's going to give me the coefficients bm, and the other formula, that is z minus z naught to the power m minus 1. So when I do that, that is going to give me the coefficients cm. This is going to give me the coefficients cm. So these are two expressions that we use to find out the coefficients. And once we get the coefficients, we can just put them back and we'll get into these two series. Or you can actually find out the coefficients a n directly from here, substitute over here, and that is going to give us the Lorenz series expansion. Is that clear?
Yes, sir. Yes, sir.
Okay. Okay, so now we'll proceed. So this is your Lorenz series. Okay, this is the Lorenz series. This is the Lorenz series. This is the Lorenz series, and these are the coefficients. These are the coefficients of the Lorenz series. Okay, so now some points that you have to remember. Lorenz series is valid even if there are no singular. Okay, my mistake. Lorenz series is valid even if there are no singularities. Okay, here I started with saying that this Lorenz series, there is a singularity. But what about if there is no singularity? In that case also no problem. The Lorenz series will be still valid. Only what happens is if there are no singularities, then the Lorenz series, if there are no singularities, the Lorenz series will reduce to a Taylor series. Okay, understood? If there are no singularities, the Lorenz series is going to reduce to a Taylor series. So this means that the Lorenz series, is a generalization. The Lorenz series is a generalization of the Taylor series. Okay, it's a generalization of the Taylor series. Or another way to put it another way to write the same thing is that the Taylor series, is a special case of the Lorenz series. Okay, so all Taylor series are Lorenz series, but all Lorenz series need not be Taylor series. Okay, so if there are no singularities, the Lorenz series is going to become simply a Taylor series. So if f is analytic everywhere within C1, that is on the annulus and within C2, then the Lorenz series reduces to Taylor series, exactly what I said sometime back. Then if we go on expanding C1 and shrinking C2 until we reach a singularity, till that domain the series is convergent. So essentially what it says is, if we use the principle of deformation of path, okay, using the principle of deformation of path, first just a second, save this. The third point, what it says is, using the principle of deformation of path. So suppose this outer, the contour, let's say I keep on expanding it outwards. I can do that, right? As long as the points, they are all analytic, as long as the new path after deformation, the new path, if it is analytic, I could go on expanding this. Likewise, I could also keep on shrinking. This inner contour. I could keep making it smaller and smaller. Till when can I do this? Till I come across a singularity. So let's say I come across a singularity over here. There's another singularity here. let's say there's another singularity here, then till here, the outer annulus till here, and somewhere till here, that is going to be the domain for the Lorentz series. Okay, so that's what the last point says. Okay, so now the proof of the Lorentz series. Okay, so I'm going to provide you with a proof of that. Whenever we have a situation like this, then the Lorentz series expansion is a valid expansion. So we will actually prove this now. Okay, the proof of the convergence of the Lorentz series. All right. So how we do that is we again take the same annulus, we'll take it, and then what we'll do is we will take an arbitrary point within the annulus. So this is the arbitrary point. This Z is the arbitrary point. Okay, so this point is arbitrary. Okay, this is an arbitrary point. Then within this arbitrary point in this annulus, using Cauchy integral formula, we get this result. Okay, using Cauchy integral formula, we get this result. But wait a minute, do we apply the Cauchy integral formula like this? Do you remember the Cauchy integral formula? Can anyone tell me? Any one of you? What is the Cauchy integral formula? You can check your notebook if you want. Anybody? Do you remember what is the Cauchy integral formula?
So integration of f of z, z minus a dz.
Okay. Integration
Is
of
equal
closed loop integration of
f of z,
yes,
z
dz
minus a
z minus z naught
equal to 2 pi I f of a.
2 pi I f at z naught, right? So this is your Cauchy integral formula. Now what is this z? What is yeah, this is this contour C. So what does the Cauchy integral formula say? What does Cauchy integral formula say? It says basically this. So suppose I have some point, okay, I have some point z naught, and this point z naught is this point z naught is the function is not defined at this point. Okay, then you can take a contour around this point. The function is not analytic. Okay, this sorry, not the function. This integrand is not analytic. The function is analytic. The function is analytic at z naught. Okay, so what I do is I take a contour. I take a contour C around this point. Then the closed loop integral of this is going to be equal to 2 pi I times the value of the function at this point. Okay, so this is what we have. Now consider this. How do you get this formula from using the Cauchy integral formula? Here, look at this. What kind of region is this? What kind of domain is this? It's a simply connected domain, right? The domain that we have here is a simply connected domain, right? Because the contour C, it's a simple closed curve. So the domain must be a simply connected domain. Here, what kind of domain is this? Is this simply connected? Is this domain simply connected? Or is it multiply connected domain? Definition of simply connected and multiply connected domain. Do you all remember?
Multiply connected.
Yes, it's a multiply connected because it's got a hole inside. No, it's got a hole inside. So now my question is this: here it's not a simply connected domain. Here we have this same scenario. Okay, the same scenario. Okay. Similarly, I'm drawing here. What is the scenario? Don't worry about the shape of the boundary because I can always use the principle of deformation. So this shape is not circular, not a problem. I can always make it circular by the principle of deformation. So let's say inside we have a hole. Okay, that means let's say there is a singularity over here. So now it becomes a multiply connected domain. Okay, now this becomes a multiply connected domain within this shaded region. So when this becomes a multiply connected domain, then say I take a point inside this domain. Okay, this point here I was calling it a z naught. Okay, any point, any arbitrary point that was z. So similarly, I take an arbitrary point over here. Okay, that arbitrary point here, this is z now. Okay, that arbitrary point, let's say that arbitrary point is also z, right? So can you still apply this Cauchy integral formula in this case? Because these two formula, this particular formula that we got here, that is for a simply connected domain, but here this example that we saw, it is not a simply connected domain. So how do we apply the Cauchy integral formula in this case? Okay, I'd like you all to take maybe a 1 minute to think about this. Each one of you just think about this. How can you apply the Cauchy integral formula in this case and we get a scenario like this, or in this case and get a formula like this? Just think about it and let me know. Take a minute, think about it. If you have figured it out how to do this, just let me know. Okay, unmute yourself and let me know. Any ideas? Anybody? Any suggestions how we can go about this? How we can obtain this formula?
Sir,
Yeah,
Sir, can we draw like a circle around the Z?
circle
And then
around this one. How will that help? How will that help?
suppose
Then
if
then it's going to become this one. Okay, if you draw a circle around this z, but how are you getting the C1 and C2? You see, in this formula we have C1. That is you're constructing another contour. Let's call that contour as, let's say, C3. Then you'll be just using the Cauchy integral formula, and the integration will be over C3. There is going to be only one integral, but in this there are two integrals. So that I
what
don't think that will work.
what if we put C1 equal to the summation of C2 plus C3, but then
Yeah, but what if, no, no, you have to justify that. Can you really do that? C1 equal to C2 plus C3, can you justify that? There is a way by which you can justify that. But what you're doing is actually you're complicating things much simpler. Very easy. All you need to do is do a branch cut. That's all. What you do is take a pair of scissors and you cut off this region. Okay, I mean not so far away from each other, cut them very close to each other. Okay, like imagine, okay, imagine that you have a pair of scissors with you, and using this pair of scissors you have cut open this part. Okay, some this region which is very close to each other. Okay, so you have basically cut open this part, and by cutting this open now you have made, earlier there were two boundaries, no? Remember I told you how to convert, how to go from, multiply connected, how to convert a multiply connected domain into a simply connected domain. Remember I told you when we discussed simply connected and multiply connected domains, I also told you how to convert a multiply connected domain into a simply connected domain. You have to make lots of cuts like this. Just make a lot of cuts like this. So by doing this cut, you're actually making is into a simply connected domain. See, only one boundary. Earlier there were two boundaries. Now you see only one boundary. You start from here, okay, go all the way here to here, and then you start from here, go all the way till here, then you go up like this, okay, and then go like this, then you go down. Oh, sorry, my mistake, it's the other way around. So start from here, go all the way here, come down till here, then you go up. Okay, then go this way, come this way, and then you go down. You see, you are on the same boundary. This is the same boundary. Okay, same thing. You can just make a cut here. Understood? So if you make the cut here, it becomes a simply connected domain. And this becomes a simply connected domain. You could have any complicated shape, any multiply connected domain. So you could have one hole here, another hole here, another hole here. So what you can do is just make some branch cuts. So maybe I'll make one cut here, then maybe another cut over here, and one more cut over here. Once I do that, so one cut here, another cut here, and one more cut over here. So now you can just check for yourself. Let's say you start from this point. You go all the way like this, go all the way like this, like this. Okay, now you go up. Okay, again, go like this, come here, like this. See, it's one single boundary. So now this has become a simply connected domain. Is that clear?
Yes, sir.
Just see how many holes are there. Okay, those many cuts you have to make. Okay, you could this same thing, no, you could also do it like this. Okay, the same domain, suppose. Okay, so we have one hole here, another hole here, and one more hole here. Instead of cutting it like this, you could also cut it like this. You could have, basically, how many holes are there? Three holes. So you need three cuts. You need one cut here, you can have another cut here, and one more cut here. This will also work. Okay, so one cut here, and then another cut over here, and another cut over here. So this will also create, you see, you start from here, start. Okay, go up like this, like this. Again, you're still in the same boundary. And see back here. So this is also a simply connected domain. So this is how we can convert a simply connected domain, a multiply connected domain, into a simply connected domain. So you just have to make a cut over here. Is that clear? So by doing this, we will be able to obtain this formula. Okay, you can see it for yourself. You can just obtain this over here. So now you see I made a cut here. Okay, let's try to work this out here. I made a cut in this part. So this point, instead of calling it as Z, I'll call it as W here. Okay, instead of calling it Z, let's say this point, I'll call it as W. So now what will happen is this contour that we have, this entire contour, that contour we'll call it as C. Okay, this entire contour we'll call it as C, and this C1 was the earlier contour and C2 is this earlier contour. So this total contour is C. So because now C encloses, C is a so since C is a simple closed curve, therefore this domain, okay, domain enclosed by C. Okay, let me write it on the other side. So since C is, this is C. Okay. So since C is a simple closed curve, simple closed curve, so therefore it encloses a simply connected domain. It encloses a simply connected domain here. So therefore, using the Cauchy integral formula, what do we have? The closed loop integral over C of f of not z, we are taking on the contour, the point that we take here is omega. So f of omega d omega divided by the z is the point that we are taking here, so omega minus z, omega minus z. Okay, so this is equal to twice pi I into f of z. So here we have again f of z is equal to 1 by twice pi I closed loop integral over c f of omega d omega f of omega d omega divided by omega minus z. This is basically your Cauchy integral formula. I have just changed, instead of z I'm using omega, instead of z naught I'm using z. That's all I'm doing here. So now if you look at this over here, C is the complete curve. Now let's say C is the complete contour. Okay, C is this complete contour. Now you can say, let's say this one we call it as L. Okay, this one we call it as L1 and this one we call it as L2. Okay, so L1 is almost the same as minus L2. I mean, when I say plus or minus, it means direction, right? Because they are very close to each other, the length of L1, length of L2 will be more or less the same. Only direction is different, so that's why I'm writing minus. So now you can say that this C can be written as this C1, or it's not equal to, it's approximately equal to this closed contour C is approximately equal to C1, is approximately equal to C1, okay, plus L2. You start from here, you go all the way along C1, then you go along L2, then C2, but you see the direction has changed. C2 is anti-clockwise, but you are traversing in the clockwise direction. So minus C2, then L1, So this is what we have. So as a result of this, the integration over C, the closed integration over C, it is approximately equal to the integration over C1, okay, minus the integration over C2, minus the integration over C2. I'm just getting the C2 over here. Then plus, now this is not a closed integral because this is not a, L1 is not a closed loop. L1 is just a segment, it's just a curve, right? So L1 and L2. So we have L1, oops, it should be over L1. So integration of the same function over L1 plus integration of the same function over L2. But now we know that L1 and L2, their directions are opposite. So this will be equal to integration over C1 minus close integration over C2, then plus integration over L1, and L1 and L2, they are opposites of each other, so minus L1. These two will get cancelled, so as a result we will have integration over C is equal to integration over C1 minus the integration over C2. I'm not putting is like the integrand is same in all the cases, integrand is same. Okay, so you can see for yourself, this is the same formula, right? F, okay, now this one is going to give me, this integration over C is going to give me f of z, right? 1 by 2 pi I into f of z, right? So 1 by 2 pi I goes over here, 1 by 2 pi I integration over C is equal to 1 by 2 pi I integration over C1 minus 1 by 2 pi I integration over C2. Okay, in the integrand is f omega d omega divided by omega minus z. Does that make sense? Is this clear to everyone?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
All right. Okay, so this is what we get. This is from the Cauchy integral formula. Okay, this is what we got. So now a little bit of manipulation is what we'll be doing. Okay, so for this first contour, for C1, for this C1 contour, this 1 by omega minus z, we will write it like this. 1 by omega minus z, we'll write it as 1 by, you are just adding and subtracting z naught. Okay, what is z naught? Z naught is right at the center of the annulus. This is where z naught is. Okay, this is where z naught is. C1, C2, and this is Z naught. I am right. C1 is outer, C2 is inner, okay, and Z naught is over here. Okay. So we have, what we do is we add and subtract Z naught, okay, and after we have added and subtracted Z naught, so omega minus Z naught you collect it, and Z minus Z naught also you collect, Z minus Z naught also you collect. So when you take minus outside, this plus is going to become minus here. So we have this. Okay. Now what you do is you take Z minus Z naught common. So when I take z minus z naught common, okay, when as I have done over here, when I take z minus z naught common, the first, this is going to give us a 1. Okay, this is going to give us 1, and over here the second term z minus z naught will be divided by omega minus z naught. Okay, let's call this equation number 2. In a similar way, over here for the second contour, C2 1 by omega minus z. So here also, this I will write as minus 1. Okay, I want to get a minus 1. To get minus 1, what you have to do is the denominator I have to write as z minus omega. Understood? No? This is what I did first. Minus 1 divided by, instead of omega minus z, I write it as z minus omega. Okay, z minus, that's going to contribute that minus sign. So we get a minus sign here. Again, we add and subtract z naught. Just as before, you add and subtract z naught. Then we collect z minus z naught and omega minus z naught here. Then you take z minus z naught to be common. So when you take z minus z naught common, the first term will get a 1 here. Second term is omega minus z naught divided by z minus z naught. Let's call this equation number 3. Is this clear? It's very simple. Okay, just some algebraic steps. That's all. All right, so 1 by z naught. This is for C1. The first one is for C1 and second one is for C2. Okay, note it down here. This is for C1 and this is for C2. Okay, so for C1 is this, for C2 is this. Okay, so now we're going to look at the geometric series. Okay, you all already are familiar with this geometric series. This is a geometric series, 1 plus finite geometric series, 1 plus q square and so on, all the way to q to the power n minus 1. This summation of a finite geometric series is 1 minus q to the power n divided by 1 minus q. Okay, and this will be equal to, I just split this, I'll get 1 by 1 minus q minus q to the power n by 1 minus q. Once that is there, then what we can do is this 1 minus q, I'll keep it on one side, and this minus q to the power n by 1 minus q, you take it to the other side. So 1 by 1 minus q is equal to 1 plus q square, this geometric series, plus q to the power n by 1 minus q. Okay, so this is just another manipulation that you have done using the sum of a geometric series. So now, we will use this value of q. Okay, for the integral over c1, for the c1 integral, the value of q will be this. Q will be equal to z minus z naught by omega minus z naught, and for integral over c2, it will be omega minus z naught divided by z minus z naught. I think I can show you why. Okay, the reason why we're doing this. I hope it's there in the next slide. No, it's not there in the next slide. So let me show you here itself. Okay, so let's say I'll draw two contours. Okay, one is C1, another one is C2. First, let me just draw both of them together. This is C1 and this is C2. Okay, so we have C1 here and C2 over here, right? So let's say, how did we choose our omega? Okay, let me refer to this. Okay, so omega is on it could be either on C1 or it could be on C2. Z is in the annulus and Z naught is inside C2. Okay, we'll keep this in mind. So Z is somewhere over here. Z is somewhere over here. This is Z, and this point is Z naught. Okay, is that clear? So this is our annulus. Now what we'll do is, let's look at only C1. Okay, let's take only C1. Let's look only at C1. Let me just carry this others also. So here we have only C1 and I'll collect C2. Okay, so this is your C1 and this is your C2. All right, so now what about omega? Omega is a point, right? As can be seen over here, omega could be a point either on C1 or on C2 because you're using this to integrate over C1 or C2. So omega could be here or here. Let's again go back here. So let's say first case is for C1. Omega, where could omega be? Omega will only lie on the contour. Okay, it will lie only on the contour. So omega is going to be here. For C1, omega is going to lie over here. Okay, so now consider this. Take this distance between the center, that is Z0, till here. We'll find out this distance. Okay, from center all the way till here. What is this distance equal to? Okay, so what is this distance equal to? This distance will be equal to, it will simply be equal to modulus omega minus Z0, right? Distance between any two points, in a complex plane, it will simply be distance between any 2 points in a complex plane. It will simply be the difference between these 2 points and taking the modulus. So all I have to do is just take the difference between these 2 points. The difference between them is omega minus Z0. Omega is here, Z0 is here. Just take the difference. Any order. It could be Z0 minus omega also, no problem. Omega minus Z0 and take the modulus. That is going to give me this distance. Is that clear? In a similar way, what will be this distance? Tell me. what will this distance be? This distance from here to here, what is this distance? Anybody?
Modulus z minus z naught.
Modulus z minus z naught. Good. This is that distance. Okay. In a similar way, here also, okay, in a similar way, from z naught till z, okay, I want to find out this distance, and this is easy. What is this distance? This distance will be again modulus z minus z naught. It will be modulus z minus z naught. And finally, you choose an omega here. Let's say I choose omega over here. I choose omega over here. I want to find this distance also from the center till this point. So what is this distance? What is this distance? Omega minus z naught. Do you agree? All of you?
Yes, sir.
This distance
Yes,
will be
sir.
omega minus z naught. Okay, good. Omega minus z naught. All right. So now next thing here, you immediately notice here. What we notice is this. Agree? Obviously, no, because z it lies on the annulus, omega it lies on the contour C1, right? So C1 enclose is the outer boundary of the annulus. So any point on C1, if you take the distance, that distance will be always greater than this distance from the center till the point in the annulus, right? So z minus z naught will be less than omega minus z naught. Fine. If that's the case, then modulus z minus z naught, modulus z minus z naught divided by modulus omega minus z naught, modulus z minus z naught divided by modulus omega minus z naught, this must be less than 1. Okay, what is the similar conclusion from here? Tell me. Anyone can tell me? Similar conclusion from here.
Omega minus z naught is less than z minus z naught.
Yes, in this case for C2, let me write this here first. This is for C1, this is for C2. Omega minus z naught is less than z minus z naught, which implies that omega minus z naught divided by z minus z naught will be less than 1. Is that clear?
Yes, sir.
Okay. Now, why are we talking about all of this? This is because you see this geometric series that we had. See, right? This geometric series expansion. Okay. So if I take Q equals Z minus, let me just get this idea here. Z minus Z naught by omega minus Z naught. This is less than 1. For C1, Z minus Z naught by omega minus Z naught is less than 1. This is for C1. Okay. So for C1, let me note it down here. Z minus Z naught divided by omega minus Z naught. This quantity is less than 1. And for C2 is the other way around. Omega minus Z naught divided by Z minus Z naught. This quantity is less than 1. Okay. So this Q, if I choose it to be this, for integral over C1, if I choose Q to be this, then this, we know that this quantity will be, the modulus of Q will be less than 1. And if you choose Q to be like this, then the modulus of Q will be less than 1. This is for C1 and this is for C2. Okay. So therefore, we have 1 by omega minus Z. Okay. Omega minus Z. 1 by omega minus Z is equal to this quantity, 1 minus Z naught by omega minus Z. This is, remember, this is for C1, okay? This is for C1 and this is for C2. This is how we have got, right? Right, for C1 and C2. Right, this one from C1, this one from C2. Okay, so this for C1, this for C2. And we know that in C1, over C1, Z minus Z naught by omega minus Z naught, this quantity, its modulus will be less than 1. And for C2, this quantity's modulus will be less than 1. Okay. So over here, in this case, we could just as well write it like this. This could be written as simply 1 divided by omega minus Z naught, times 1 minus, this quantity is Q, right? For C1, this quantity, this is Q, right? It's the same quantity. This is Q into 1 minus Q. Likewise, for this also, this is equal to 1 divided by, so we have a Z minus Z naught. We have a Z minus Z naught, and inside we have 1 minus omega minus Z naught by Z minus Z naught, omega minus Z naught by Z minus Z naught. For C2, this is your Q. So again, we have a 1 minus Q. All right, everyone?
Yes, sir.
Yes, sir.
So therefore, for C1 we have, that's the same thing, okay? I'm writing this in terms of Q. For C1 we have, this is equal to 1 by the omega minus Z naught into 1 minus Q. And we know that here it is guaranteed. The way we have chosen this Q, it is guaranteed that the modulus of Q is less than 1. Okay? So now again, we use this expansion. This is 1 by 1 minus Q is equal to this entire thing. 1 by 1 minus Q, 1 by 1 minus Q, we write it as the expansion, the geometric series expansion. This is what we get. Okay, so 1 by omega minus Z is 1 by omega minus Z naught into 1 minus Q plus Q square plus so on till Q to the power n minus 1 plus Q to the power n by 1 minus Q. In a similar way, okay, and then here again you replace back. Okay, for C1, what is Q? For C1, what is Q? Q is equal to Z minus Z naught by omega minus Z naught, substitute it back. Okay, for C1, Q is equal to Z minus Z naught divided by omega minus Z naught for C1. This is what it is, and then you just substitute it back. So 1, okay, 1 plus Q, that is Z minus Z naught by omega minus Z naught, and there is another omega minus Z naught which you multiply, so 1 by omega minus Z naught, and this omega minus Z naught into this will give us a square here, okay, and so on. Q to the power n minus 1, so Z minus Z naught to the power n minus 1 divided by omega minus Z naught to the power n minus 1 times omega minus Z naught, that is going to give us omega minus Z naught to the power n. And then you have Q to the power n omega z minus z naught, okay, divided by omega minus z naught whole to the power n, right? Into 1 by omega minus z. So this is what we get. Okay, you can verify for yourself. This is exactly what we are going to get. Then minus 1 by omega minus z. This is again going to be equal to this. Okay, this is what we wrote here. Okay, the minus sign comes from here, and this is 1 minus q. So in a similar way, 1 by 1 minus q, you expand this as using the geometric series, and this is what you will get. Right? So for C1 and C2, this is what the denominator looks like. So this original one, this is, remember, this is from the CIF. Remember, this is from the CIF, from the Cauchy integral formula. We had already arrived at this. For C1, 1 by omega minus z. So 1 by omega minus z is equal to this. Okay. So the first integral, that is integral over C1. So 1 by twice pi I integration over C1 f omega d omega by omega minus z. This 1 by omega minus z, we write it like this. So we have, this is the first term. This one comes from here. Then this one comes from here, because there is a z minus z naught. So we'll get a z minus z naught here. And omega minus z naught square will go over here. So likewise, we'll get, this one is going to give me this quantity, and this term is going to give me this quantity. So we'll get an expansion like this. Okay, so we'll get a series of integrals like this. So this is a series of integrals. So now this integral, okay, this integral, will define it as 1 by twice pi I into f of integration f of omega d omega omega minus z naught. This entire quantity, we'll just call it as a0. Remember, Lorenz says this is how we had defined, right? This is how I had defined, no? N, and so on. Put 0, 1 by 2 pi I integration f omega d omega divided by omega minus z naught. N is 0, omega minus z naught. So f omega by omega minus z naught. So that is your a0. Okay. Let me write it down here itself first so that we can refer to it on this slide itself. Give me a second. So we have an is equal to 1 by 2 pi I closed loop integral f of omega d omega divided by omega minus z naught to the power n plus 1. I'm just writing this over here so that I can refer to this in a later slide. Done. Okay, now you can see here, this one, if you put n equals 0, we have f omega divided by omega minus z naught. You'll get this one. There's a 1 by twice pi I. So together, this is going to give me a0. Okay, so together it's going to give me a0. Then you put n equals 1. You put n equals 1. So we have 1 plus 1 is 2. So f omega by z omega minus z naught squared, right? And 1 by twice pi I is already there. So this is going to give us a1. And there is a z minus z naught outside, right? That is, this entire thing is going to give us a1 z minus z naught, and so on. So this is going to give us an minus 1 into z minus z naught to the power n minus 1. And finally, whatever is left behind, this one, this part, whatever is left behind, that we'll just give it some name. That is like the residue that is left behind. This one, this part, we'll just call it as Tn. These are residual terms. Okay, these are the residual terms. Okay, so here an, okay, an is equal to 1 by twice pi I integration over C1 f omega by omega minus z naught to the power n plus 1. And this Tn, this is the residual terms. This is the last term, the very last term which is left, 1 by twice pi I times this last term, that is going to be Tn. Okay. All right, next, in a similar way, we again proceed to the second integral. The second integral, this is what we have. Okay, so the second integral, it becomes, so minus 1 by twice pi I f omega by omega minus z is equal to So 1 by omega minus z is equal to minus 1 by omega minus z is equal to this entire thing. So substitute. So this minus gets absorbed inside. So we get 1 by twice by I. Z minus z naught, I'm writing it as z minus z naught to the power minus 1. Okay. F integration of f omega d omega. Right. This is what we get. Then the next term and the next term and so on. So we have all these different terms. So we now define this. Okay, so this is going to be your a minus 1 into z minus z naught to the power minus 1. This one, 1 by twice pi I into this integral, that is equal to a minus 2 into z minus z naught to the power minus 2, and so on. This is 1 by twice pi I into this integral is a minus n and z minus z naught to the power minus n. And whatever is now left behind, I'll call it as t minus n. T minus n is this quantity, this last quantity that we have here, this last quantity, that is your t minus n. So that is like your residual terms. So this is what we have. Okay, so now we just have to subtract. We have to take the difference between, or we have to just take the sum of these two integrals, because already the minus sign is incorporated over here. So f of z is equal to this minus this. The first integral, it gives me this summation, and the second integral minus the second integral, it gives me this summation. So it's just a matter of f of z is equal to just take this sum and this sum together. Okay, so using this we will get this. So now I could just call everything. Okay, we could just call it as ak. We can use some index ak into z minus z naught to the power k. Over here, what is the value of k? K goes from minus n to n plus 1. You can see here the smallest value, the smallest power is minus 1 minus n, and the highest power is n minus 1. So this smallest power, the smallest power is minus n, so that's why k starts from minus n, and the highest power is n minus 1. So k, it takes the maximum value that it can take is n minus 1. Then the coefficient we call it as ak z minus z naught to the power k. Then this tn, the residual term, and t minus n, this is the residual term, we can just take them together. So the next challenge is what we have to show is, because this is still not the Lorenz series, because what is the Lorenz series? If you look back, this is what we got. What should be the Lorenz series? Let me go to that slide which contains the Lorenz series. This is what the Lorenz series should look like, right? The Lorenz series, it should be f of z equals summation n equals minus infinity till plus infinity a n z minus z naught to the power n. This is what the Lorenz series is, right? But what have we got so far? Okay, so this is what we have got so far. So immediately you can see here the Lorenz series is supposed to be like this. Here, instead of n, I'm putting k here. Okay, if k goes, that is, if n tends towards infinity, so k will go from minus infinity to plus infinity, because infinity minus 1 is also infinity. So if I take the limit, suppose I take the limit as n tends towards infinity. Okay, in that limit, what will happen? This summation, if I take this as the limit, then this summation, what we will get, k is equal to minus infinity all the way to plus infinity. So we have ak z minus z naught to the power minus k. And then what about these two terms? These two terms will have a t infinity and will have a t minus infinity. But here in the Lorenz series, there is no extra term. That means these two terms, they become 0. These two terms, they vanish. So what we have to next show is, what do we need to show? We need to show that if n tends towards infinity, then tn and t minus n, both of these should tend towards 0. If n tends towards infinity, tn and t minus n, both of them, they should tend towards 0. Is that clear? Is that clear? If we can show that this is the case, then these two will vanish, and as a result, we'll be left behind with only this summation. And that is basically your Lorenz series. So that's the next challenge. Next, we have to show that Tn and T minus n will tend towards 0 as n tends towards infinity. Is this understood?
Yes.
Okay, so now tell me, can anyone tell me how do we make sure that this happens? How can we? Is there any method? Is there any way by which you can actually prove this? Using what? What can we use? How can we show this? How can we show this? Using what do we will we be able to show this? Can anyone think about this? Is there any theorem or any result that you have learned where if you make something infinity, another quantity goes towards 0? Does anybody remember? Yes. This is where your ML inequality again will come. We have to invoke the ML inequality once again, and we have to show that Tn and T minus n, they will both tend towards 0 as n tends towards infinity. Is that clear? Is this understood?
Yes.
So this is what we'll be doing next, okay? So now, since f omega is analytic, it is bounded. It is analytic means it has got some bounds. So f omega must be less than m, okay? So also, this quantity is less than 1 over C1 and this quantity is less than 1 over C2. We have already seen that, right? We have already seen this happening over here. This quantity is less than n1 and this quantity is less than 1 in case of C1 and C2 respectively. Okay, so we've already seen that. So this implies over C1, this quantity, let's say we call it as sigma. Okay, let's call it sigma. And over C2, this quantity, let's say we call it as sigma. Then sigma lies between 0 and 1, right? This quantity, if I call it as sigma for C1 over C1, this quantity, if I call it as sigma, and this quantity, if I call it as sigma over C2, then sigma will always lie between 0 and 1, because if a quantity lies between 0 and 1, it is guaranteed that it is less than 1. And it is greater than 0 because it has to be greater, because it's modulus, no? Modulus means it has to be a positive quantity. So we are looking for a positive quantity which is less than 0. Sorry, we are looking for a positive quantity which is less than 1. Any positive quantity which is less than 1, it must lie between 0 and 1. So that's why if we call this as sigma over C1 and we call this as sigma over C2, then sigma will lie between 0 and 1. Okay, so finally this omega minus z is equal to z minus omega. The order does not matter. Let's say this is less than delta r, okay, because we are not considering a infinite domain, right? We are considering a finite domain, so there is going to be a upper limit to the difference, to the range that we're going to have, to the distance between omega and z. Okay, so then by ML inequality for Tn, this is Tn. So omega z minus z naught by omega minus z naught to the power n, f omega by omega minus z. This will be less than, this quantity is sigma, right? For C1, this quantity is your sigma. So this is going to give us sigma to the power n. Okay, this will be less than, right? It has to be less than. Then f omega is bounded. Okay, it gives us m, and then omega minus z, okay, that is going to give us delta r, okay, times 2 into pi into r1, because we are taking over contour over C1. That means contour over C1, what is the length? ML inequality, that L part is the length of the path. The length of the path will be the circumference of the circle. The circumference of the circle is 2 pi into r1. So this is what we have. So 2 into pi into m into r1. So 2 into pi into m into r1 divided by delta r into sigma to the power n. So this is what we get. So we have got an upper bound for Tn. Okay. In a similar way, for T minus n, we get something like this. Okay. So therefore, we have this f of z is equal to this. Tn has got an upper bound. T minus n also has got an upper bound where sigma is between 0 and minus 1. Then as n tends towards infinity, Tn will tend towards 0. As n tends towards infinity, Tn will tend towards 0. Because you see sigma is a quantity which is less than 1. Any quantity which is less than 1, if you raise it to a power, it will become smaller and smaller. Agree? So let's say I consider, let's say sigma to be equal to 0.1, right? Sigma is 0.1. Then what is sigma square? It will be 0. Sigma is 0.1. Then what is sigma square? It's 0.01. What is sigma cube? It will be 0.001. What is sigma to the power 4? It will be 0.0001, right? So this sigma, it lies between 0 and 1, right? So any quantity which lies between 0 and 1, if you raise it to some power, it's going to get smaller and smaller and smaller. Okay, so sigma to the power n. Okay, as n increases, okay, as n increases, sigma to the power n will decrease. So as n tends towards infinity, this sigma to the power n will tend towards 0. The sigma to the power n will tend towards 0. So as a result, Tn and T minus n, it will tend towards 0. So that's it. That's the proof that we're looking for. So T and T minus n, they will tend towards 0. So as a result, in this one, as n tends towards infinity, f of z, only this summation will remain. That summation, n tends towards infinity, so we'll have minus infinity till plus infinity. K is anyway a dummy index, so we might as well replace k with n, not a problem. So n going from minus infinity till plus infinity, k again replaced with n, so a n z minus z naught to the power n. So this is your Lorenz series expansion. So that's the proof that the Lorenz series also converges. Is this clear? Everyone?
Yes, sir.
Okay, so I think we can stop here.
Sure.
This is 2:18. I took half an hour extra because of obvious reasons. Yesterday we had missed the class, and I told you that I will take a extended class. So we will stop here. Okay, see you all next week. Do you have any questions? You may ask me.